Using the property of determinant and without expanding, we have to prove that the value of this determinant is equal to 0. Let's begin with the left hand side. Here we have x plus a, y plus b and z plus c in third column. So if we add second column into the first one, then we will get same quantities. So the preferable operation is C1 gives C1 plus C2. That means we have to multiply plus 1 with the second column and add into the first column. So A1s are A, B1s are B and C1s are C. In this operation, our second and third column will be as it is, and our first column will be x plus a, y plus b and z plus c. So as you can see, first column and third column are same, so the value of determinant will be 0. Is your required right hand side. Ta-da! Using the property of determinant and without expanding, you have to prove that the value of determinant is equal to 0. Very good. So first of all, let's write down left hand side. So here we have a symmetric matrix. So preferable operation is C1 gives C1 plus C2 plus C3. So first of all, let's add second column in the first one. So here we'll get B minus C, C minus A and A minus B. Similarly, it's time to add the third column, first one. So C minus A minus B plus B minus C. So in this operation, our second and third column will be as it is, and your first column will be A, B, B and C, C cancel out, so it will be 0, same as 0 and 0. So here our entire first column is 0. So we can say about the value of determinant will be 0. Is your required right hand side. Ta-da! Using the property of determinant and without expanding, we have to prove that the value of determinant is equal to 0. So let's write down left hand side. So here I already simplified the third column's element, right? Now, as you can see, the remaining element in the third column is given in the second column. So the preferable operation is C3 gives C3 plus C2. So let's add our second column into the third column, plus BC plus CA and plus AB. So in this operation, our first and second column will be as it is, and third column will be AB plus AC plus BC, same element. So from the third column, we can take common AB plus AC plus BC. So here we will get AB plus AC plus BC. Again, first two columns will be as it is, and third column will be 1, 1 and 1. Now what? Your first column is same as third column. So we can say the value of determinant is 0, which is your required right hand side. Ta-da! Using the property of determinant without expanding, you have to prove that the value of determinant is 0. Let's begin with the left hand side. See, this is a special kind of a determinant which is known as skew symmetric determinant. So let's take a minus common from the first row. You will get -1 and your first row will become 0 minus a and b. Similarly, let's take minus common from the second row. Get -1 square and second row will be a, 0 and c. Similarly, with the third row, नहीं तो बिचारान खोटो ना लागे. So here we'll get -1 whole cube minus b minus c and 0. And we know that -1 cube is -1. Let's take an operation of interchanging row with the column. So your first row will become your first column. Second row will become your second column. Third row will become your third column, which is exactly same as our determinant. If we say this is your delta, then here we'll get minus delta. Or we can say our delta is 0. Hence proved. Always remember, odd order of skew symmetric determinant is always 0. And order શું હતું? 3 cross 3. Therefore, the value of determinant is 0. Done? Using property of determinant and without expanding, we have to prove that the value of determinant is equal to 4 times a square, b square and c square. Let's begin with the left hand side. So here we have our left hand side. As you can see, we can take a common from the first row. So let's multiply a with the determinant and your first row will be minus a, b and c. Similarly, we can take b common from the second row. So multiply b with the determinant and your second row will be a minus b and c. And third row, you can take c common. Multiply c and third row will be b and minus c. Right? We can take common ABC from the first, second and third row. Right? But another steps thoda bati jase. Let's take R1 gives R1 plus R2. I am trying to get 0 at A11 and A22. So question can be easily done the shortest way. So let's write down ABC as it is. Your second and third row will be as it is. So let's put as it is. Now first row will be A1s are A minus B1s are B plus C. So this will become 0, 0 and 2C. So now we just have to expand with respect to first row. This ABC will be as it is. And the sign of the first row is plus, minus, plus. And their elements are 0, 0 and 2C. So we don't have to worry about the minor of these two zeros. Let's find out minor of 2C. And for that, we have to ignore first row and first column. Now let's cross multiply. B with A will give us AB minus A with minus B will give us minus AB. So here we'll get AB plus AB, which will be 2AB. So here we'll get 4 times A square, B square, C square, which is required right hand side. Ta-da! Using the property of determinant and without expanding, we have to prove that the value of determinant is equal to A minus B, B minus C and C minus A. So without wasting time, let's begin with the left hand side. Two things you should notice that in first column we have 1, 1, 1, which can easily convert into 0 by row operation. Second thing, to get A minus B factor, the preferable operation is R1 gives R1 minus R2. So we have to multiply minus 1 with the second row and add into the first row. 1 minus 1s are minus 1. b minus 1 is a minus b, and b square minus 1 is a minus b square. Similarly, to get b minus c, preferable operation is R2 gives R2 minus R3. That means we have to multiply minus 1 with the third row and add into the second row. So here we'll get minus 1 minus c and minus c square. In these two operations, our third row will be as it is, right? And our first row will be the 0, a minus b, and a square minus b square, or we can say a minus b and a plus b. Similarly, second row will be 0, b minus c, and instead of b square minus c square, we can say b minus c and b plus c, right? So now we are ready to take common a minus b from the first row. So we have to multiply a minus b with the determinant, and your first row will be 0, 1 and a plus b. Similarly, from the second row, we can take b minus c common. The second row will be 0, 1 and b plus c. Your third row will be as it is. Yes, don't forget to multiply b minus c with the determinant. Okay, now this a minus b and b minus c will be as it is. Let's expand our determinant with respect to our first column. So their sign is plus, minus and plus. Their elements are 0, 0 and 1. We don't have to worry about the minors of 0 and 0. We just have to find minor of 1. You have to ignore third row and first column. Let's cross multiply. B plus c with 1 will give us b plus c minus 1 with a plus b. So this a minus b and b minus c will be as it is. And here we'll get b cancel out. We will get c minus a, which is your required right hand side. Ta-da! You have to notice that we have 1 in the first row, which can easily convert it into 0 by column operation. And to get a minus b, preferable column operation is c1 gives c1 minus c2. That means we have to multiply minus 1 with the second column and add into the first column. So here we'll get 1 minus 1 is a minus 1, b minus 1 is a minus b, and b cube minus 1 is a minus b cube. Similarly, to get b minus c, the preferable operation is c2 gives c2 minus c3. So let's multiply minus 1 with the third column and add into the second column. So here we'll get 1 minus 1 is a minus 1, c minus 1 is a minus c, c cube minus 1 is a minus c cube. So in this operation, our third column will remain as it is. Our first column will be 0, a minus b and a cube minus b cube. If we apply the formula of x cube minus y cube, which have the factors of x minus y, x square plus xy plus y square, then it will be a minus b, a square plus ab plus b square. Here, similarly, your second column will be 0, b minus c and b minus c, b square plus bc plus c square. Yeah? Now, we can take common a minus b from the first column. So here, we have to multiply a minus b with the determinant, and your first column will be 0, 1 and a square plus ab plus b square. Similarly, we can take b minus c common from the second column. 0, 1 and b square plus bc plus c square. And third column will be as it is. And don't forget to multiply b minus c with the determinant. Our a minus b and b minus c will be as it is. Let's expand our determinant with respect to first row. So their sign are plus, minus, plus, and their elements are 0, 0 and 1. We don't have to worry about the minor of 0 and 0 because 0 into anything will be 0. Let's find out minor of 1 by ignoring its row and its column. So now cross multiply. B square plus bc plus c square ones are square plus bc plus c square. Then minus a square plus ab plus b square ones are. Okay. Now let's simplify. This a minus b and b minus c will be as it is. Here b square will cancel out, and let's rearrange the terms and get b square minus a square and bc minus ab. So again a minus b and b minus c will be as it is. And c square minus a square become c minus a and c plus a, plus we can take b common from the rest of the two terms. So here we'll get c minus a. So as you can see, a minus b minus c still navra. We can take c minus a common. Here we'll get a plus b plus c. Tada! This is your required right hand side. Using property of determinant and without expanding, we have to prove that the value of determinant is x minus y, y minus z and z minus x into xy plus yz plus zx. Let's begin with the left hand side. Here we need to get factor of x minus y, and for that the preferable operation is r1 gives r1 minus r2. Let's multiply minus 1 with the second row and add into the first row. So here we'll get y minus 1s are minus y, y square minus 1s are minus y square, and zx minus 1s are minus zx. Similarly, to get y minus z, the preferable operation is r2 gives r2 minus r3. That means we have to multiply minus 1 with the third row and add into the second row. Here we'll get z minus 1s are minus z, z square minus 1s are minus z square, and xy minus 1s are minus xy. Right? So in this operation, our third row will be as it is, and first row will be x minus y. Instead of x square minus y square, we can write down x minus y and x plus y. And to get x minus y, we can take minus z common. So here we'll get x minus y. Similarly, your second row will be y minus z. Instead of y square minus z square, write y minus z, y plus z. And let's take minus x common, get y minus z. So as you can see, we can take x minus y common from the first row. So we have to multiply x minus y with the determinant, and your first row will be 1 x plus y and minus z, y minus z from the second row. We have to multiply y minus z. Second row will be 1 y plus z and minus x, and your third row will be as it is. Now what? Let's try to get z minus x. r1 gives r1 minus r2. That means multiply minus 1 with the second row and add into the first row. So 1 minus 1s are minus 1, y plus z 1s are minus minus y minus z, and minus x minus 1 are plus x, right? So this x minus y and y minus z will be as it is, and your first row will be 0. Y will cancel out. Let's take minus common, so we can get z minus x, and again take minus 1 common, so again we will get z minus x. Your second and third row will be as it is. We are ready to take z minus x common from the first row. So now we get x minus y, y minus z, and z minus x. So your first row will be 0, minus 1, and minus 1. And again, your second and third row will be as it is. This x minus y, y minus z, and z minus x be as it is. Let's expand our determinant with respect to first row. Sign of the first row is plus minus plus. Their elements are 0, minus 1, and minus 1. We don't have to worry about the minor of 0 because 0 into anything will be 0. So let's find out the minor of minus 1. Ignore first row and second column. Let's cross multiply. xy ones are xy minus z into minus x will give us plus xz. Now to get the minor of minus 1, so to cross multiply z square with 1, z square minus z will multiply with yz will give us minus zy minus z square. So here z square will cancel out. These three quantities will be as it is, and here we'll get xy plus xz plus zy. Ta-da! Which is your required right hand side. In this question, using the property of determinant and without expanding, you have to prove that the value of determinant is pi x plus 4 into 4 minus x the whole square. Let's begin with the left hand side. So here we have one symmetric determinant. So let's collect all the elements in the any one row or column. Let's collect in the first row. For that, the preferable operation is R1 gives R1 plus R2 plus R3. So first of all, let's add second row in the first one. Here we'll get plus 2x plus x plus 4 and plus 2x. And then add third row, the first one. Here we'll get plus 2x and plus x plus 4. So in this operation, our second and third row will be as it is, and first row will be pi x plus 4, pi x plus 4, pi x plus 4, right? So we can take common phi x plus 4 from the first row. You have to multiply pi x plus 4, the determinant, and your first row will become 1, 1, and 1, and rest of the two rows will be as it is. Now we get 1 in the first row, which can easily convert it into 0 by column operation. So let's use first column to get 0, A12 and A13. And for that, the preferable operation is C2 gives C2 minus C1. That means you have to multiply minus 1 with the first column and add into the second column. 1 minus 1s are minus 1, 2x minus 1s are minus 2x, 2x minus 1s are minus 2x. Similarly, C3 gives C3 minus C1. You have to multiply minus 1 with the first column and add it to the third column. So here we'll get same quantities. 1 minus 1s are minus 1, 2x minus 1s are minus 2x, and 2x minus 1s are minus 2x. So here 5x plus 4 will remain as it is, and your first column will remain as it is. Now let's move to the second column. It will be 1 minus 1 0, x plus 4 minus 2x minus x plus 4, 2x minus 2x will be 0. Similarly, third column will be 0, 0 and minus x plus 4, or we can say 4 minus x, right? So this 5x plus 4 will remain as it is. Here we have lower triangular determinant, and its value can be find out by multiplying its principal diagonal elements. So 1 into 4 minus x into 4 minus x. So here we'll get 5x plus 4 into 4 minus x the whole square is required right hand side. Ta-da! Using the property of determinant and without expanding, prove that the value of determinant is equal to k square into 3y plus k. Let's begin with the left hand side. Now to simplify, let's collect all the elements in the any one row or column. I am going to collect in the first row, and for that preferable operation is R1 gives R1 plus R2 plus R3. So let's multiply plus 1 with the second row and add into the first row. So here we'll get y ones are y plus k ones are y plus k, again y ones are y. Similarly, multiply plus 1 with the third row and add into the first row. So again y ones are y ones are y, and y plus k ones are y plus k. In this operation, our second and third row will be as it is, and first row will be 3y plus k, y plus k, and 3y plus. Okay, so we can take common from the first row 3y plus k. We have to multiply 3y plus k with the determinant. So your first row will be 1, 1 and 1. Second and third row will be as it is. Again, we have 1 in the first row, which can easily convert it into 0. So let's use first column to get 0 at A12. The preferable operation is C2 gives C2 minus C1. That means you have to multiply minus 1 with the first column and add into the second column. Here we'll get 1 minus 1s are minus 1, y minus 1s are minus y, y minus 1s are minus y. Similarly, to get 0 at A13, the preferable operation is C3 gives C3 minus C1. You have to do the same thing. Multiply minus 1 with the first column, add into the third column. You will get same quantities, minus 1, minus y, and minus y. So in this operation, our first column and y plus k will be as it is, and second column will be 1 minus 1 0, y will cancel out, we will get k, and again y will cancel out, we will get 0. Third column will be 0, 0 and k. So now dy plus k will be as it is, and if you see carefully, we have lower triangular determinant, and its value can be found by multiplying its principal diagonal elements. So 1 into k into k, or we can say we will get k square into 3y plus k, which is your required right hand side. Ta-da! Using the property of determinant and without expanding, we have to prove that the value of determinant is equal to a plus b plus c the whole cube. Without wasting time, let's begin with the left hand side. Here we have our left hand side. To get a plus b plus c, let's try to get this factor in the first row by taking operation r1 gives r1 plus r2 plus r3. So let's multiply second row with the 1 and add into the first row. So here we'll get 2b1s are 2b, b minus c minus a 1s are b minus c minus a 1s are 2b. Similarly, multiply third row with the 1 and add into the first one. So get 2c1s are 2c, again 2c1s are 2c, b minus a minus b. So your first row will be a plus minus b plus 2b plus b plus c. Similarly, plus b plus c and a plus b plus c. And rest of the two rows will be same. So we can take common a plus b plus c from the first row. So your first row will be 1, 1 and 1, and rest of the two rows will remain as it is again. So here we get 1 in the first row. So let's use a11 to get 0 at a12 by taking operation c2 gives c2 minus c1. That means we have to multiply minus 1 with the first column and add into the second column. So 1 minus 1s are minus 1, 2b minus 1s are minus 2b, and 2c minus 1s are minus 2c. Similarly, to get 0 at a31, the preferable operation is c3 gives b minus c1. Multiply minus 1 with the first column, add into the third column. You get same quantities minus 1, minus 2b and minus 2c. Now, our a plus b plus c will be as it is, and first column will remain as it is. Second column will be 0, b minus 2b will be minus b minus a, and 2c minus 2c will be 0. Similarly, third column will be 0, 0, and c minus 2c will be minus c minus a minus b. So again, a plus b plus c will remain as it is, and here we have lower triangular determinant. Its value is obtained by multiplying its principal diagonal elements. So 1 into minus b minus c minus a into minus c minus a minus b. Or we can say a plus b plus c will remain as it is. Here we have minus a minus b minus c the whole square, which is equal to a plus b plus c the whole square. So here we'll get a plus b plus c whole cube, which is required right hand side. Ta-da! Using the property of determinant without expanding, prove that this determinant is equal to 2 times x plus y plus z the whole cube. Let's begin with the left hand side. Let's collect all the elements in the first column. For that, the preferable operation is c1 gives c1 plus c2 plus c3. That means to multiply plus 1 with the second column and add into the first column. So here we'll get x 1 x, y plus z plus 2x 1 y plus z plus 2x, x 1 again x. Now same thing we have to do with the third column. Y 1s are y, then plus y plus z plus x plus 2y. So our first column will be x plus x, y plus y, and 2z, or we can say 2x plus 2y plus 2z. Same quantities we will get in the rest of the elements, and second and third column will remain as it is. So we can take common from the first column 2 times x plus y plus z. We have to multiply 2 times x plus y plus z, and your first column will become 1, 1 and 1. Rest of the two columns will remain as it is again. Now we get 1 in the first column, which can easily converted into 0 by row operation. So let's try to get 0 at a21 in first row. So the preferable operation is R2 gives R2 minus R1. That means we have to multiply minus 1 with the first row and add into the second row. So here we'll get 1 minus 1 is a minus 1, x minus 1 is a minus x, and y minus 1 is a minus y. Same thing we can do with the third row. We can get 0 at a31 using first row by operation. R3 gives R3 minus R1. That means we have to multiply minus 1 with the first row and add into the third row. We get same quantities, minus 1, minus x, and minus y. So here 2 times x plus y plus z will remain as it is, and your first row will also remain as it is. Second row will be 1 minus 1, 0. X will cancel out, we will get x plus y plus z. Y will cancel out, we will get 0. Similarly, third row will be 0, 0 and x plus y plus z. So as you can see, 2 times x plus y plus z will remain as it is, and here we have upper triangular determinant, and its value can be easily found out by multiplying its principal diagonal elements. Here 1 into x plus y plus z into x plus y plus z, right? So finally here we'll get 2 times x plus y plus z the whole cube, which is your required right hand side. Ta-da!